Good morning. I am Dr. Krishna. I welcome you all to Digital E-Learning Process DCE Government of Karnataka. Today I am going to cover on algebra, in which basic concepts of binary operations and basic concepts of rings, and also the importance of this ring as a fundamental object in algebra. Let's see that first of all, binary operation. Binary operation refers to the two elements of a set. Result of the two is also in the same set. Binary operation refers to the calculation that combines the two elements of the set so as to produce another element for the same set. The binary operation star on a non-empty set A are functions from A cross A to A. The binary operation which is also mapping from A cross A to A. It is an operation of two elements of the set whose domain and codomain are in the same set. A binary operation is also a function on G which assigns an element of G to each ordered pair of elements in G. For example, multiplication and addition are two binary operations. Let us see that binary properties of binary operations. An operation on a non-empty set A which contains closure property. If A belongs to A, B is also belongs to A star B belongs to A. Addition, multiplication and subtraction are also the binary operations on each of the sets of natural numbers, integers, rational numbers, real numbers and complex numbers. But the addition, multiplication, subtraction that take place on the set of all irrational numbers is not a binary operation. Along with the division is also not a binary operation on a set of natural numbers, integers, rational numbers, real numbers and complex numbers. So we have 5 axioms in the binary operations. One is closure property, associative property, existence of identity, existence of inverse and commutative property. All these are holds good, so we shall call it as a Abelian group. First, let us see that closure property. An operation star on a non-empty set A has a closure property if A star A belongs to A there, and also A star B belongs to A provided A star B is an element of A again, that provided A and B are elements of A. That is, if we combine any two elements in the group under the binary operation, the result is always another element in the group. The set of integers under addition holds good for this property that. But odd integers are not a binary. Odd integers are not a holds good, are not satisfied under addition of this closure property. The associative property of binary operation holds if for any non-empty set A, we can state that A star B of star C equal to A star of B star C. For example, the set of integers under addition also holds good. That under multiplication of this matrices also holds good this associative property. In function composition is also holds good this property that. Suppose n be the set of natural numbers and multiplication be the binary operation. This is a property of all groups that. Existence of identity, if A be the non-empty set and star be the binary operation on A, an element E is the identity element of A belongs to A. If A star E equal to A equal to E star A is an identity element under addition. If the binary operation is addition, E is equal to 0. For multiplication, it is E equal to 1 is the binary identity element. For example, instead of integers, 0 is an identity element under addition, and in rational numbers under multiplication 1 is an identity element under multiplication. In matrix multiplication 1 is also identity element. That this is property of all groups. That existence of inverse, if a binary operation star on a set A which satisfies A star B equal to B star A equal to E for all A comma B belongs to A. A inverse is also invertible if for A star B equal to B star A equal to E. A inverse is B. One is invertible element when star is multiplication. Inverses are unique, that is each element has exactly one inverse and no two distinct elements have the same inverse. For examples, so in integer system under addition the inverse of x is minus x. In rational number system the inverse of x is 1 over x. In integer system n number of integers the inverse of x is n minus x. And last property of this abelian group, commutative property. A binary operation star on a set commutative, set A is commutative if A star B equal to B star A for all A comma B belongs to A. For example, let addition be the binary system. For A equal to 8, B equal to 9, A plus B equal to 17, that equal to B plus A. Note on this, abelian groups are groups which have the commutative property A star B equal to B star A for all A and B are in G. This is so familiar from the ordinary arithmetic on real numbers. So along with that, another property, that distributive property, we have a left distributive property as well as right distributive property with respect to addition there. And let us see that introduction about ring theory. A ring is an important fundamental concept in algebra which includes integers, polynomials and matrices as some of the basic examples. The philosophy of this course is that modern algebra notions play an important role in mathematics and in application to areas such as physics, computer science, economics and engineering. This course emphasizes the application of technique. Ring theory has applications in number theory and geometry and many fields that many. So basic concepts before going to ring, that we have concepts of group. In concepts of group, that non-empty set G is said to be group if it's satisfied by 4 axioms. So one is closure, associative and identity, and also along with inverse that. And also with the commutative law also satisfied, which is called a abelian group. And also we have a semi-group under multiplication, a non-empty set G closed under some associative property. Associative property is called semi-group. So that one is example set of integer under addition as well as multiplication is semi-group, but that a set of integers under subtraction is not a semi-group since it is not associative. Subgroup, let G be a group and H be a non-empty subset of G, then H is a group under the binary operations defined in G. Note that a non-empty subset H of the group G is subgroup if and only if AB inverse belongs to H for all A comma B belongs to that subgroup. So we have these are the examples there, examples of a group that. And let us see that definition of a ring. An algebraic structure R plus dot is a ring if R is a non-empty set and addition and multiplication are two binary operations such that addition is an abelian group. R plus is an abelian group. That is, we have to see that closure property, associative property, identity, inverse, commutative property. All these holds good that R plus is an abelian group. And this R dot is a semi-group. So that in which multiplication are here, that are non-zero is a semi-group in which closure and associative properties are holds good under multiplication. Also R plus dot under multiplication is distributive, so that we have a left distributive as well as right distributive, that is for A comma B comma C belongs to R, so that one is left distributive law holds good, another one is right distributive law holds good. So remarks on this, there need not be multiplicative inverses. Multiplication need not be commutative. It happens only B is not equal to BA. So that let's see that commutative ring or abelian ring. If R is a abelian ring, if R is ring and commutative law with respect to whole, with respect to multiplication in 8, then R is called commutative ring. R is called commutative ring if for all A comma B belongs to R, AB equal to BA. Another concept in ring theory, ring with unity or identity. If R is a ring and which contains multiplicative identity 1, then R is called a ring with unity, that is 1, that is not equal to non-zero element. Examples of this ring, so that one is Z, integer system, rational number system, real number system. These are all the Z is subset of Q is subset of R, are all commutative rings with the 1. And also that set of integers, n number of systems, as n number of elements in that integer system is a commutative ring with the 1. The set of all even numbers is a commutative ring without unity. The set of rational numbers, set of real numbers, set of complex numbers are all examples of commutative ring with the unity. Also that the set of matrices of order n by n over the field of rational numbers is non-commutative ring with the unity there. So another example that Z6 is also commutative ring with the unity. And for any ring R, the set of functions f R to R, real number to real number, is a ring. By definition, this composition holds good that this also a ring with the commutative ring with the unity. That if R is a ring and X is a variable, then the set R of X is called polynomial ring over R. The set of even integers is a ring without unity, but the set of odd integers is not a ring. Let X be non-empty set and let P of X be the set of all subsets of X. Let addition and multiplication is defined as A plus B equal to A minus B, union of B minus A. And also we have A composition B equal to A intersection B. Then X is a commutative ring with unity, where X is the identity element. Since X is A intersection X equal to A for all A belongs to power set. So consequences of this definitions. So we have a 3 consequences. One is if 0 is the additive identity of R, then A dot 0 equal to 0 dot A equal to 0 for all A belongs to R. Another consequence is A of minus B equal to minus A into B is equal to minus into AB for all A comma B belongs to R. And last consequence is minus A into minus B equal to AB. So we shall see this proof of these consequences in the study material of this course. So thank you, India.